Flipped Friday. Today I'm going to be giving you a video lecture, which is going to be an overview of where we're going with the Tableau combinatorics that we've been learning so far in Math 533. So today I'm going to talk about a Littlewood Richardson rule for Grassmannian Schubert varieties. Let's get started. So algebraic combinatorics, the way that it's understood today, goes back to Giancarlo Roda, who was a professor at MIT. He said, combinatorics is an honest subject. No Adels, no sigma algebras. You count balls in a box, and you either have the right number or you haven't. And we'll see that lots of people have had the right number and some haven't. So what's a partition? We can think of a partition as a way of placing balls into boxes. So here I've placed 7 balls into 5 boxes. And since the balls are not numbered, right, they're identical. The boxes are not numbered, they're identical. So how do I tell different configurations apart? Well, it's just about the multiplicity of how many balls go in each, go in a box. So you might as well put the most full box at the top and then the next second most full and so on. And now you can describe your partitions. And of course we would describe this as 5, 2, 1, 1, 0. 3, 2, 1, 1, 0. So a tableau, as we've been thinking about it, we're going to shift our paradigm slightly. We're going to think of it as a way to fill boxes. So here I'm going to fill these boxes, not the bubbles, in such a way that we never have an empty box directly above or left of another. So here's an example. We're going to track the order that we add the boxes. Okay, so I start with my bubbles, and this is really giving me a skew tableau. Now I'm going to add a box. So the first box gets the number 1. The second box, because I picked this one, it's to the right, it'll also get the number 1. The next box is to the right again, so it'll get the number 1 as well. Now I picked a box to the left. So again, I'm just doing an example, I just picked a box. So because I went to the left, I'm going to put a number 2. That way, as I start to think about, is this reversible, these numbers, the 3 1s and then the 2, are going to tell me exactly the order I took things off in. So I took all the 1s off. That was the last thing I'm going to do, is take the 1s off. So it was the first thing I did. I put the 1s on from left to right, so I know I can take them off from right to left. So let's pick another box, another 2 here, and then backed up, so there's a 3. So this is an example of what I would call a tableau. I'm not allowing any numbers in the boxes the way that we have done in class in a lot of cases. I'm specifically doing it this way, where I kind of lay them down in a specific order. And these numbers will have properties that we'll see. So here are the 11 different ways I could do it for this shape. So you can check, it's good to kind of look through that all of these I could do in exactly this way. So when you take off the 3, make sure that there's a 2 to its right. So here, this 3 is here, there has to be a 2 weakly to its right. So here or here, because if the 3 were here, well, then I would have called it a 2. So for this example, these 11 tableaux, they're all the ways of laying down 3 boxes, backing up 3 boxes, backing up 1 box. That backing up is something new. So you can check that these examples all work and that these are all the examples. Now I'm going to put another filter on the type of tableau that I'm considering. So I'm not just considering all tableau with 3 1s, 3 2s, and a 3. I'm not just considering all the ones that I can kind of get from this laying down procedure. I'm going to consider the ones that I'll call lattice. What does it mean to be lattice? That means if you read the tableau from right to left, you've always encountered at least as many i's as I plus 1s. So here I have encountered a 2. Have I encountered as many 2s as 1s? No, I haven't seen a 1, so this guy is not lattice. On the other hand, if I look at, let's say, this guy, I first encounter a 1, so I've seen as many 1s as 2s. When I get to this column, what do I have? I have 2 1s and a 2. So that works. Here, when I get to this column, I have 3 1s and 2 2s. Okay, I've got more 1s than 2s. When I get to this column, I have equal numbers of 1s and 2s that are to the right. So that counts. And now I've added a 3. So this one is lattice. So you can pause here if you want and just do a check. Read this condition to yourself another time. Pause the video and see if you can tell which of these 11 tableaux is actually lattice. So the first thing you should do if you were eliminating things is just look, if the first thing I encounter is not a 1, there's no way it's lattice. So these guys are out. So if you didn't feel like doing the big example from before, you could pause now. There are 4 objects left. Which of them is lattice? So here, I check this one. 1, that's good. Okay. 1, 2, okay, 2 1s and a 2, that's fine. When I get here, I have 2 1s, 2 2s, and a 3. That's fine. If you think about it, what we're really saying is that like when you count the number of 1s, the number of 2s, the number of 3s, and so on, it's a partition. So this would be the partition 2 2 1, which is fine. But now, when I get this 2, I have 3 2s, but I've only seen 2 1s. So this guy's not lattice. You can check these other 3 are. So the answer is there are 3. 3 of these 11 tableaux are lattice. So that's the combinatorics that we're looking at for today. But that was just sort of a digression. We've been doing combinatorics all semester. What about the context? Okay, well, let me give you the context. For today, I'm only going to give you this half of the story. This is the half of the story that we're going to do after spring break. So let's look at the first half. The Littlewood Richardson rule. I've mentioned it, I've alluded to it. Let's see what it is. Ian MacDonald, who's in Cambridge, has some great quotes. One of my favorites is, one starts out in life trying to do mathematics and winds up doing combinatorics. So let's start with the mathematics. We haven't seen it yet. How many lines in space meet 4 given lines? That's a question, an enumerative geometric question that people were asking in the 1800s, and they knew how to answer this one. Well, sort of they knew. So first of all, what's space? Well, it's what you think it is. It's a room. Okay, and what are 4 lines? Well, here you go. And if any of you guys is interested in running a math circle, this is a really great math circle activity. If you have some masking tape in 4 different colors and you have a small room, you can tape up 4 lines in space. And you're asking how many other lines can touch all 4 pieces of tape. And so what you do is you take a really long broomstick and you have the kids try to line the broomstick up to touch all 4 pieces of tape. Pro tip, only give one kid a broomstick at a time, because you don't want it to turn into some kind of sword fighting match. Okay, so they'll do it too, and they'll get the right answer. It's remarkable. Let's do it very concretely. So if you want, you can pause, and you could just do this explicitly. Let's just, figure this one out. How many lines do you think meet these 4 given lines? All right, so assuming you don't want to pause, I'm going to make some observations. So my first observation is that the orange and the purple line meet in the plane z equals 0, okay? So they intersect. And the blue and the cyan lines meet in the plane x equal -1, so they intersect. So that's your hint. So if you didn't pause before, you could pause now. Now, can you find lines of intersection? Well, I hope you found at least one. So I think this one's probably the most obvious, and this is the one the kids usually go for first. You have a point of intersection, another point of intersection, and 2 points defines a line. So the line through those 2 points of intersection, that's one line that touches all 4 of the colored ones. There's another line though. Keep in mind that 2 lines span a plane. So the orange and purple span the plane z equals 0, and the blue and cyan span the plane x equal -1. And those 2 planes intersect in a line. So that's your other line. And that one's a little harder to see. And depending on how you did the tape, that one might not exist in your room, but it exists in the plane in general. So when we're thinking about these sorts of questions, one thing that you could say is, well, what if you took the same line twice? Well, don't do that. That's silly. Well, what if you took 2 lines parallel? Well, parallel lines meet at infinity. So when we start doing geometry, we're going to do projective space. Exactly because we need those parallel lines to meet. So we'll assume something called general position, which is, you didn't take 3 coplanar lines. Okay, that would be bad. That would sort of break the problem a little bit. And then we'll also work in projective space to avoid the problem of parallel lines. So 2 is the answer. I didn't get in projective space. So, okay, question. How many lines meet 4 given lines in space? Well, we saw the answer is 2. But that's only if the first 2 lines intersect and the second 2 lines intersect. And Schubert, in his thesis of enumerative geometry in 1874, building on the work of many people before him, he described this thing he called the principle of conservation of number. And he said, because the answer is 2 in this special case, it's actually 2 in general. And David Hilbert, at the turn of the 20th century, called on this to be made rigorous. The problem consists in this: to establish rigorously and with an exact determination of the limits of their validity those geometrical numbers which Schubert especially has determined on the basis of the so-called principle of special position or conservation of number, by means of the enumerative calculus developed by him. So Schubert's wrong in general. Principle of conservation of number is not a real thing, and if you try to apply it blindly, it's just false. Interestingly, in every single instance that Schubert applied it, the principle held and he was correct. So there was something he was doing that he was not able to articulate that made this work and made his counting actually work. And that's what Hilbert wanted us to find. And that led to many beautiful advances in mathematics. And so one way that we think about it in a more modern way is we think about the Grassmannian. So the Grassmannian we'll spend a lot of time on. It's k-dimensional subspaces of n space. This is a projective variety, and it's okay if you don't know what projective or variety means at this point. Just think of it as k-dimensional or full rank k by n matrices, if you like. So we're going to fix a partition that lives in a rectangle. So it's a k by n minus k rectangle. That's where the partition has to live. It sort of has to be bounded in this way. And n and k are the same n and k as up here. And we're also going to fix what we call a complete flag. This is just a nested sequence of linear subspaces. The dimension, it's complete because the dimension of fi is I. If we start skipping steps, then we have a partial flag. But for now, we have a complete flag. Okay, and we're going to take a basis for Cn. How about E1 up to En? Then a flag that we could take is just take subsets of this from the front, right? F1 will be the span of E1, and F2 is the span of E1, E2, and so on. That will definitely give us a flag. And it's fine to keep just that example in mind for now. So what's a Schubert cell? Now we're getting pretty complicated. So a Schubert cell, it's an open set of the Grassmannian. It's the set of all of these k-dimensional subspaces of n space that intersect our flag nicely. Okay? So here's a way I can think of it. In this example, k is 5, so I have 5 rows in my matrix, and n is 12, so I have 12 columns. Now, this matrix is going to have to be full rank, and you can see my example is. This example is specifically chosen to mirror this partition. So you can see these 5 zeros here, 3 zeros, 2 zeros, 2 zeros, and 1 zero highlighted in red. So this is giving me the codimension, in a sense, for the space spanned here. So it's going to tell me the codimension of this Schubert cell. So I think of these, all the matrices that have this form where stars are the free entries. These are called pivots here with the 1. They're sort of fixed. So the entries that could be free but aren't are the red zeros. And that's why I say it's the codimension. It's the stuff that we've killed. The dimension is all the stars. So the codimension is the size of this partition, but you can see the actual partition showing up here, and the combinatorics is starting to manifest. So, okay, all matrices that look like this, right, where these stars can be any non-zero numbers, but you've got to have the ones and the zeros, that's going to fill up our Schubert cell. And we can take the closure in the Zariski topology, and that's what a Schubert variety is. The Grassmannian itself, the set of all k-dimensional subspaces, is the union of these Schubert cells. They all look something like this when we put them into canonical form. So a Schubert variety, as I mentioned, is going to be the closure in the Zariski topology. It's irreducible, closed, and its codimension is the size of the partition, right? And we see that from those zeros. So Schubert varieties are also unions of Schubert cells. They decompose in this nice way, and in fact, the Grassmannian itself is a Schubert variety. So these are the sorts of geometric objects that we want to study, and the example that we had before of lines in space can be expressed in terms of Schubert varieties. But before we do that, let me talk about intersecting them. So sometimes it's easy to intersect Schubert varieties. I'll give you an example. So I'm going to take a partition here and the standard flag. So when I say that, I mean the canonical basis, and you're taking the first Q of them, and that's FQ. That's our flag that we're defining. And then this is just the example that we just had. So this is how I describe the Schubert cell. But that's a choice. I could choose differently. So for example, I could take mu to be some other partition, and I could take the opposite flag. Now, F1 is just En. F2 is En minus 1, the span of those. So I'm taking the flag from the other end. Okay, that's coming from the other direction. When I do this just in terms of the matrix, just in terms of the linear algebra, it sort of looks upside down, maybe transposed from what I had before. So this Schubert cell corresponds to the partition 6, 5, 5, 4, 2. And you can see the 6, 5, 5, 4, and 2, but in a different way. So it turns out that if I take a Schubert cell and what we call an opposite Schubert cell, again, the difference here is the choice of this flag, which is a choice I can make. These two varieties, it turns out, meet transversally, we'll talk about that condition later, in one point. And you can probably see the point. Now, what's a point? A point is an element of the Grassmannian, a k-dimensional subspace of, well, in this case, a 5-dimensional subspace of 12 space. And you can see what it is. What is the only matrix that looks like this and like this? Here, all the red zeros correspond to all of the stars, and all these red zeros here correspond to all these stars. So when we stack those together, this is the only matrix that we get. It is spanned by the 3rd, 6th, 8th, 9th, and 11th basis elements. So this is one point. This one 5-dimensional subspace of 12 space is the only thing that is both in this Schubert cell here and this opposite Schubert cell here. So the point of this example is just to say that if you set your example up really nicely, it's very easy to intersect Schubert varieties. But keep in mind, I have made some very special choices. I've chosen this flag and this flag in the same exact literal way that Schubert chose to make his first 2 lines intersect and his second 2 lines intersect in order to make his computation simpler. I've done the choice of flag to make my computation simpler. And now we understand the principle of conservation of number by passing to cohomology. So what is cohomology? Well, it's a way of enriching the structure of a topological space. So we turn it into a ring. So homology gives you a group structure, but cohomology gives you a ring structure, in fact, an algebra structure. The cohomology is a graded ring. We're going to have the kth graded pieces, and there's a multiplication that we can do, which sort of brings us up in degree in the way that we expect. So for any irreducible closed subvariety of codimension k, so we often work with codimension, it's more natural in a lot of reasons, we're going to have an element of the cohomology ring, okay? And this is going to be the class of X, okay? It's an element in this ring, which means we can multiply these things together. And in fact, if we make good choices, so we take 2 varieties here and these z's are sort of more varieties, if X and Y is, the intersection is proper and transversal, those are important technical conditions, but supposing we have them, then, and they meet in these varieties, this is how we decompose the intersection, then the cohomology tells us that. Okay? So cohomology gives us a way to pass from geometry to algebra. So now, instead of doing a computation in terms of geometry and looking at these spaces, literally, we just take their classes in this mysterious cohomology ring, we take a product, and then we write it as a sum. Well, that would be easy as long as this cohomology ring has a basis, because writing things as sums is non-trivial. And do you know what's unique? Well, Borel knew it was unique. So Borel described the cohomology classes for partial flag varieties. And for the Schubert class, so the Schubert variety, we get these Schubert classes, sigma, lambda. And here's the crux. This Schubert variety, the geometric object depends on the choice of the flag. Which lines, right, intersect depends on the choice of the lines. But the cohomology class does not depend on the choice of the flag. It doesn't matter which 4 lines in space you took, as long as you didn't do something silly like 3 coplanar ones. That's what proper and transversal is helping us do. So this is Schubert's principle of conservation of number. And moreover, Borel showed that these classes, specifically for Schubert varieties, give a basis for the cohomology ring. So if you want to understand intersections in the Grassmannian, it is enough to understand it on a basis, and this is the basis of choice. In particular, multiplication in the cohomology ring is determined by the multiplication of these basis elements. And because these numbers are counting objects in an intersection, we know they're non-negative integers. They count something. So going back to our example and taking this theory, applying it back, given a line, there is a Schubert variety, which represents the set of all lines in R3 that meet L, okay? So again, projective space, that's why this is a 4, not a 3, but you understand why this is a 2. So in projective space, we have this Schubert variety. Now, what are we trying to do? If we want to count lines, just lines, that's going to be this Schubert variety, that are incident to 4 given lines. Well, here are my 4 given lines. I want to compute this intersection. Well, it depends on the choice of L1, L2, L3, and L4. But the multiplicity doesn't. So I can take the cohomology classes. Okay, these are all the same thing. I'm just taking the 4th power of this class, which just means literally this Schubert class, 4th power. Okay, it's a basis. Write it out. You're done. The answer is 2, because look. So there's a dictionary here, which is how I translate the geometric objects into Schubert varieties. But once we get past that dictionary, we have this computation. So the next step is to demystify this computation. How do I compute in the cohomology ring? Oh, sorry, 2 is the class. Well, for this, we're going to use the ubiquitous Schur polynomials. So we've discussed symmetric polynomials. We've discussed the fact that the Schur polynomials are a basis for the ring of symmetric polynomials. And we've observed the fact that if you multiply Schur polynomials together, you get some structure constants. That's what we'll call, these are the Littlewood Richardson numbers. There is a map from symmetric polynomials to the cohomology ring of the Grassmannian that sends these lovely Schur polynomials to the Schubert classes, or kills them if you went outside the rectangle. It's a ring homomorphism, which means that we can translate the structure right across. So it's not a coincidence that I've written this with the same notation that I wrote for the Schubert classes, because they are the same coefficients. Again, with the caveat that you haven't gone outside of your k by n minus k rectangle. I say ubiquitous, where do they come up? So I've hinted at this before, and I'll just write it down a little formally right now. So Schur polynomials are characters of irreducible representations of the general linear group. If we tensor two irreducible representations, we can decompose it as a sum of irreducible representations, and the multiplicities that arise are these Littlewood Richardson numbers, the same ones. On the other hand, Schur functions are Frobenius characters of irreducible representations of the symmetric group. If we induce from a Young subgroup up, we do it on the irreducibles, sometimes called the spect modules. We can decompose that into irreducibles again. And again, the coefficients that occur are exactly the Littlewood Richardson numbers. So these come up in many contexts, geometrically and representation theoretically. And there are several more as well. And the Schur polynomials, as we've seen, are the generating polynomials of semi-standard Young tableau. This is the example that we did before in class. So the number of lines incident to 4 given lines, if we've done the dictionary and we know what Schubert varieties we're interested in, well, now we can just say, what I'm trying to do is I just need to expand this guy to the 4th power. That's this Schur polynomial in 2 variables. That's where these 4 and 2 are coming from. So in 2 variables, I need to expand it, right, in the Schur basis. So if I wrote it out, I would get this. But now this does not fit in a 2 by 2 rectangle. This does not fit in a 2 by 2 rectangle. This one does. So the only surviving term is this, and I see that there are exactly 2 lines. So I can do the computation in Schur polynomials, which is something we could throw on the computer, right? But we're not going to do it that way. We're going to follow Littlewood and Richardson. So if you notice, the title of their paper does not include the word combinatorics. Group characters in algebra is what they were studying. So they said that these Schur structure constants that we're after, which we now call Littlewood Richardson numbers in their honor, is the number of what we now call Littlewood Richardson tableau. And now what are those? Well, I'm going to define it by example. Suppose I have this Schur polynomial multiplied by this Schur polynomial, and I want the coefficient of this Schur polynomial. It turns out it's 3. Why is it 3? Well, what Littlewood and Richardson said was, we take the shape determined by mu. Okay, so we take the shape mu and we construct this shape, which is lambda, my big partition, subtracted mu. So you see the skew shape here. Okay, For new, we're going to take the standard filling, which is all ones in the first row, all twos in the second row, all threes in the third row, and so on. Okay, this gives us the weight. And now we're going to put these boxes over here, subject to the lattice conditions. And before we saw in our example, we got 3. That's why it's 3. This is the combinatorial rule that Littlewood and Richardson came up with. And they did a lovely big example in their paper, and their paper has an error in the example. It's kind of fun to go through that and look at it, and you're like, oh yeah, that one and that one. I think they had 2 that they missed in their computation. But nonetheless, their rule is correct. And they called it a theorem, but maybe theorem was an overstatement. In fact, they even state in the paper that they don't have a general proof. They can only do it in a special case, which is the Peary rule we did before. And in fact, even in the Peary case, they don't actually do it completely in that case. So the theorem's not due to them, but this beautiful, amazing statement absolutely is. Gordon James, who wrote a fantastic book on representation theory, wrote, "The author was once told that the Littlewood Richardson rule helped to get men on the moon, but it was not proved until after they had got there. The first part of the story might be an exaggeration, but the second one definitely is not. So let me tell you the history of the proof of the Littlewood Richardson rule. It came 40 years later in the thesis of a graduate student in Cambridge. G. Thomas gave the first complete proof in 1974, exactly 40 years later. I don't have a picture of Thomas because despite this remarkable achievement, the internet does not seem to remember him. I think he did not go on to stay in math for that long, which is really a shame because I can't imagine what other beautiful theorems he could have given us. So Schutz and Berger in France, 4 years later, published the first proof. So this was published after Thomas's, but I think Schutz and Berger was most likely not aware of Thomas's work. And in fact, what makes this more remarkable is that his proof is almost identical because the time was just right for this problem that had stayed open for so long to be solved because all the key ingredients were there. All one had to do was realize it. And of course, that's a big thing to do, but it's interesting that both of these people did it around the same time and exactly in the same way. So both of the proofs are based on the work of Robinson. About 4 years after the Littlewood Richardson rule, he gave a proof that's published. It's not really a proof by any reasonable standards. There are huge gaps and a few errors in it, but it's very difficult to read. So the gaps weren't noticed right away. It took a while to notice them because it is an incredibly difficult paper to read. But actually, Robinson came first, so let's just insert him here. Okay, great. And Shenstedt, we've talked a lot about Shenstedt's insertion. He did this in 1961. He was not working on the Littlewood Richardson rule at all. He wasn't doing representation theory. He was a computer scientist. But he came before Schutz and Berger, so let's bump him out of the way. And the last ingredient, of course, we've talked about Don Knuth. And in 1970, he generalized what we now call the Robinson-Shenstedt insertion to become the Robinson-Shenstedt-Knuth insertion. And he proved a lot of amazing things and added this idea of Knuth equivalence that we spent a lot of time on into the mix. And those are the ideas that Thomas and later Schutz and Berger realized were all that was needed to prove the Littlewood Richardson rule. So here's Thomas's proof. There is a bijection between semi-standard Young tableau of shape mu. Remember, this gives us, if we add these up, we get a Schur polynomial for mu. Add these up, we get a Schur polynomial for nu. So we're multiplying 2 Schur polynomials. And what do we get? Disjoint union becomes a sum. These are numbers. These will become your coefficients. Add this up and you get a Schur polynomial. So it's the proof from the book. We couldn't ask for a better conceptual proof. So Don Knuth famously says, an algorithm must be seen to be believed. So let me show you the proof. So here's an example. Here's a tableau for a running example of shape mu. Here's a tableau of shape nu. I need to set up a bijection where I get a Littlewood Richardson, a standard Young tableau, that'll be this one, and a Littlewood Richardson tableau. So what I do is I start with this tableau is here, this one. And now over here, I've got this tableau. And this is where I'm going to record the action. Now first what I'm going to do is I'm going to turn this into a word by uninserting. And that's easy enough. So we pull off that box. What happened here? The 6 is going to unbump the 4, unbump the 2, and come off. So that's what we get, right? The 6 and the 4 came down. And we record a 3 because we pulled it out of the 3rd row. I'm going to record a 2 because I'm going to pull this out of the 2nd row. It's going to bump down here. And there we go. I pulled off a 4. That's what popped out. So it's reverse insertion. I'm going to pull off this box next. So I'm doing this in a canonical way. I'm going to pull off this box. It's in the 2nd row, so I'm going to record a 2, and the 4 is going to unbump that 2. Okay, the 2 is going to have to come off next. The 2 is going to unbump that 1, so I'll have a 1 down here, and I came out of the 2nd row. And now all these guys are just coming out of the 1st row, so they're pretty straightforward. Now what I'm going to do is I'm going to insert. I'm going to insert the 2 into this diagram. Wherever the new box is, I'm going to put this as my recording box for where it went. So here the 2 is going to bump the 3, which bumps the 5, which lands here. My new box will be recorded here. So that's what I do. Now I'm inserting a 4. The 4 can just land. New box. I'm inserting a 6. The 6 can just land. New box. The 1 will have this bumping path. The 2 will have that. 4, 2. The theorem is that what I get is a Littlewood Richardson tableau. And this is my standard Young tableau. So I said this is the best ever proof. Actually, there's so many best ever proofs. Littleman gives a beautiful proof using the path model. If you're familiar with that from representation theory, it's a phenomenal proof. Gasharov gave a really slick proof. Stembridge gives a 4-page proof. Knudsen-Tau's puzzles, one of the puzzles is seen here, gives a proof where you can really see a lot of symmetry that we couldn't see before. And this is what they use to prove the saturation theorem. So it's obviously, I mean, I don't think you can prove the saturation theorem using this model. So clearly this is an amazing proof to have. And then Ravi Vakil has these checkerboards that he uses to give a geometric Littlewood Richardson rule, which is phenomenal as well. So these are just brilliant and awesome. And if you want to look at any of these proofs for your final paper for the class, I'd be delighted for you to pick up any of those. They're fantastic proofs. And now we'll finish just by going back to our question. How many lines in space meet 4 given lines? Well, by the principle of conservation of number, if we intersect the first 2 and the second 2 intersect, then the answer is 2 and we know which 2 lines. Or we could say, using the theory of cohomology rings, all we have to do is make a computation in cohomology, which is to take the 4th power of the class of lines meeting a given line, and we see that the number of lines inside of that is 2. Or we could use symmetric functions, and we could say that actually we're just taking the 4th power of this Schur polynomial and looking for the coefficient of this Schur polynomial inside of it. Therefore, the answer is 2. Or we could use the Littlewood Richardson rule and count lattice tableau. So what that means is every time we want to intersect another line, we just add a box. So we start with nothing, 1 box, only way to do it. Add another box. These are the 2 ways to do it. Add another box. Okay, these are all the ways, but keep in mind we have to fit in a 2x2 rectangle, so these guys are out. Add another box. And then filter, because we only need to stay inside of a 2x2 rectangle. So the Littlewood Richardson rule gives us these as our answer. So there are 4 ways to think about this. The most geometric, moving to cohomology, using the classes and representatives of them, which is Schur polynomials, which is much easier than using the actual ring there. We use the ring of symmetric polynomials, or just get down to the answer with the combinatorics. And so that's really what we're doing here with all the combinatorics that we're learning, is we're learning how to multiply Schur polynomials, we're learning how to compute in cohomology classes, and we're learning how to intersect varieties. And then we'll see later that we can do this in a much more general context, but unfortunately, we don't have all the answers there. So we'll pick this up on Monday, and on Monday, we'll go over some generalizations of the Littlewood Richardson rule and of insertion and RSK into different contexts that you might want to look at for your group presentation that will be due before spring break. So that is it. I hope this was enjoyable and that you learned something, and we will see you in class in person on Monday.